was August 2018 inside the Rio Centro Convention Hall at Rio de Janeiro. The air had become thick with anticipation, an unspoken tension that stretched taut. It was the eve of the International Congress of Mathematicians, a rare gathering held only once every 4 years. The spotlight was on the impending announcement of the Fields Medals, the highest honor in mathematics. The identities of the winners were shrouded in secrecy. The Fields Medal, often called the Nobel Prize of Mathematics, is awarded every 4 years at the International Congress of Mathematicians to mathematicians under 40. It's an honor that highlights remarkable achievement and potential, pointing to groundbreaking work that could redefine how we think about mathematics. This year, one name was seen as the strongest contender in the corridors of universities from Princeton to Kyoto. Many believed that it was not a question of if, but of when. The name was Peter Scholze. When he is finally called to the stage, the man who appears is unassuming. At 30 years old, he is one of the youngest ever to receive the award. He is tall and slender, with a quiet demeanor that seems at odds with the monumental scale of the recognition. He appears slightly uncomfortable with the bright lights and the applause, a private person suddenly at the center of the mathematical world. The citation is read aloud, honoring him for the revolution that he launched in arithmetic geometry. He had ignited a complete shift in a field that studies the deepest connections between numbers and shapes. How does one person, before his 31st birthday, rewrite a branch of mathematics that has occupied the most extraordinary minds for centuries? Let's find out. Peter Scholze was born in Dresden, Germany, on December 11, 1987, and grew up in Berlin in a home where the language of science was his native tongue. His father is a physicist, his mother a computer scientist, and his sister would go on to study chemistry. This environment provided a natural setting for a mind drawn to logic and structure. He attended the Heinrich Hertz Gymnasium, a high school in Berlin with special focus on mathematics and science. It was a place where, as he later recalled, you were not being an outsider if you were interested in mathematics. His exceptional talent was apparent early. He participated in the International Mathematical Olympiad over years and returned with 3 gold medals and 1 silver. But the true beginning of his journey happened away from any competition. At 16, he learned that Andrew Wiles had, a decade earlier, proven Fermat's last theorem. The problem is famous for its deceptive simplicity. The equation x to the power of n plus y to the power of n equals z to the power of n has no whole number solutions when n is greater than 2. Scholze was determined to understand the proof. He quickly found that the solution was a labyrinth of modern mathematics, connecting disparate fields in ways no one had previously mastered. In an interview, he remembered how he understood nothing, but found it really fascinating. This moment was formative. Instead of giving up or starting with a textbook on algebra, he began a process of learning in reverse. He started with the conclusion, Wiles's monumental proof, and worked backward, identifying and then learning each piece of mathematics he needed to comprehend the whole. He never formally learned subjects like linear algebra in a classroom. Instead, he simply assimilated them when he needed them to understand a more complex structure. He was not just interested in solving the puzzle of Fermat's theorem. He was captivated by the pieces themselves, the strange and beautiful objects called elliptic curves and modular forms that Wiles had used. The structures were more interesting than the problem they were built to solve. After high school, Scholze enrolled at the University of Bonn, where he continued to pursue his interest in number theory and geometry. His unusual method of learning continued to set him apart. His classmate and future colleague Eugen Hellman recalled that Scholze never took notes during lectures. He did not need to. He could absorb the material in real time, understanding it at a level so deep that he would not forget it. He moved through the university curriculum at a startling pace, completing his bachelor's degree in 3 semesters and his master's in another 2, a 5-year program finished in 2.5 years. In 2010, while still a 22-year-old graduate student supervised by Michael Rappaport, a gossip started to spread through the mathematics community. It concerned a notoriously dense 288-page proof known as Harris-Taylor, a cornerstone of the Langlands program. The rumor was that a student in Bonn had rewritten the entire proof in just 37 pages. That student was Peter Scholze. His paper was more than just a summary or a condensed version. He had found a new perspective, a clearer route that avoided some of the most challenging parts of the original argument. It was a stunning demonstration of clarity and power. Jared Weinstein, a number theorist now at Boston University, was shocked that someone so young could produce something so advanced. This paper announced the arrival of a new kind of mathematical mind, one focused not just on following complex arguments, but on rebuilding them from a better foundation. The University of Bonn recognized the scale of his talent. In 2012, shortly after he completed his doctorate, the university appointed him a full professor. At 24, he became the youngest W3 professor in Germany. The German academic system is known for its formal, structured progression. To bypass the traditional postdoctoral track and grant its highest professorial rank to someone so young was an extraordinary step. The university understood they were not just hiring a promising mathematician, they were securing a figure who would define the field for a generation. To understand the work that won Scholze the Field's medal, we must venture into the strange and beautiful world of numbers that he has made his own. Our familiar number system, the real numbers, can be pictured as a continuous line. We start with the whole numbers, say 1, 2, 3, and so on, and the fractions that live between them. But this line is full of holes. Numbers like pi or the square root of 2 are not fractions, yet they have a definite place on the line. The real numbers are what we get when we complete the rational numbers, filling in all these gaps. The way we measure distance on this line is simple. The distance between 5 and 7 is 2. But what if there were other ways to measure distance? This is the question that leads to the p-adic numbers. Let's pick a prime number p, for example, 5. In the world of 5-adic numbers, the size of a number is not determined by how far it is from 0, but by how many times it is divisible by 5. Numbers expressed as higher powers of a base are considered smaller than the base itself. For example, 25, or the square of 5, is smaller than 5, and 125, the cube of 5, is smaller still. The more factors of 5 a number has, the smaller its 5-adic size. This seems bizarre, but it provides a powerful lens for number theory, where the prime factors of a number are of central importance. Mathematicians visualize these number systems as a tower. At the bottom level, we might group all numbers by their remainder when divided by 5. This is called modular arithmetic. On the next level, we group them by their remainder when divided by 25, then 125, and so on infinitely. In this system, two numbers are considered close if they share the same room high up in this tower. The 5-adic numbers are the result of completing the rational numbers using this new idea of distance, just as the real numbers complete them using the standard 1. There is not just one p-adic system, but an infinite family of them, one for every prime number. There are 2-adics, 3-adics, 7-adics, and so on. Over the years, Scholze has become so comfortable in these alternative universes that he finds our everyday numbers to be the strange ones. He has said that he finds real numbers much more confusing than p-adic numbers. These p-adic worlds are central to arithmetic geometry. However, they come with a major difficulty. They are mixed characteristic systems. Imagine a number system. In some systems, you can keep adding 1 forever and never get back to 0. This is like our regular numbers, and we call this characteristic 0. Now imagine another system where if you add 1 to itself a certain number of times, let's say p times, you actually get 0. This is like a clock where after 12 you go back to 1. This is called characteristic p. A mixed characteristic system is a bit like having 1 foot in each world. The main number system behaves like characteristic 0, but when you look at its residue field, which is what you get when you work with remainders after dividing by p, that part behaves like characteristic p. Problems can be really tricky in this mixed setting because you're dealing with 2 different types of behavior at once. However, if both the main system and its residue field follow the same characteristic, meaning either both characteristic 0 or both characteristic p, then things often become much simpler to understand and solve. For decades, mathematicians have sought a bridge between these 2 worlds. In his 2012 doctoral thesis, Peter Scholze built one. He introduced a new class of objects he called Perfectoid Spaces. These are intricate, fractal-like geometric structures that exist in the p-adic realm. Their creation, the construction of a new conceptual language. The key function of perfectoid spaces is an operation called tilting. This allows a mathematician to take a problem from the difficult mixed characteristic world and tilt it into an equivalent problem in the simpler equal characteristic world, solve it there, and then untilt the solution back to the original setting. It is like having a translator that can take a piece of literature written in a dense, archaic language and render it perfectly in a modern, simple one without losing any of the meaning. The first major application of this new machinery was Scholze's proof of a special case of the weight monodromy conjecture, a major conjecture in the geometry of solutions to polynomial equations. This became the core of his thesis, but the conjecture itself was only the beginning. He had not just solved a problem, he had created a tool of such general power that it would soon find, in the words of collaborator Anna Cariani, applications in a million other directions that weren't predicted at the time just because they were the right objects to think about. After the Fields Medal in 2018, the honors continued to accumulate, cementing his position as one of the leading mathematicians in the world. In 2019, he received the Great Cross of Merit of the Order of Merit of the Federal Republic of Germany. He was also appointed a director at the prestigious Max Planck Institute for Mathematics in Bonn, his academic home. But his focus was already elsewhere, on projects that aimed at an even deeper level of mathematical reality. One of the grandest visions in modern mathematics is the Langlands program, proposed by Robert Langlands in the 1960s. It is often described as a grand unified theory of mathematics. a vast web of conjectures connecting the world of numbers analyzed by number theory with the world of symmetry and waves analyzed via representation theory and harmonic analysis. In a fitting turn of events, the proof of Fermat's last theorem that had so inspired Scholze as a teenager was itself a proof of a small piece of the Langlands program. Now, armed with the powerful tools of Perfectoid Spaces, Peter returned to this grand vision. His work has allowed mathematicians to extend the program's reach into new, higher-dimensional territories, revealing what he called an entirely new suite of reciprocity laws. Scholze's results showed that the Langlands program is deeper than we thought, it's more systematic, it's ever-present. Even as he was expanding one of mathematics' great programs, Scholze was beginning two new projects that aim at an even more fundamental level of unification. The first, developed with Bhargav Bhatt of the University of Michigan, is called Prismatic Cohomology. Cohomology is a set of tools for studying the properties of geometric shapes, often by examining their holes. Over the decades, mathematicians have developed many different cohomology theories, each suited for a different context. These different theories are like the individual colors of a rainbow. Prismatic cohomology is the prism itself, a single unified structure that contains all the different colors and shows how they relate to one another. The second project, undertaken with Dustin Clausen of the University of Copenhagen, is even more ambitious. It is called Condensed Mathematics. This project seeks to rebuild the very foundations of topology, the branch of mathematics that studies properties of space that are preserved under continuous deformation. For decades, mathematicians have struggled with technical problems that arise when trying to combine the tools of algebra with the study of topological spaces, like topological groups. Condensed mathematics proposes to replace the fundamental object of a topological space with a new concept, a condensed set. This new foundation is designed from the ground up to work seamlessly with algebraic methods. This work is at the absolute frontier of the field, and one of its core proofs was so complex that Scholze himself was not entirely certain of its correctness after he first worked it out. So he and his collaborators launched the liquid tensor experiment. They created a challenge to formally verify the proof, using a computer proof assistant called Lean. Over 6 months, a team of mathematicians translated his argument into computer code, and in May 2021, the computer confirmed the proof was correct. For all the abstraction of his work, Peter Scholze is described by colleagues in remarkably human terms. He is seen as grounded and generous, someone who, despite his towering intellect, never makes you feel that he's, somehow so far above you. He is known for the exceptional clarity of his talks and papers, and for his willingness to explain his ideas to students and younger researchers. He is, however, a deeply private person and has found his growing celebrity status a bit overwhelming. He prefers to focus on the mathematics itself, which he approaches with a unique mental discipline. He often works without writing anything down, preferring to hold entire structures and arguments in his head. This forces him to distill his ideas to their cleanest and simplest possible form. As he explained it, you have only some kind of limited capacity in your head, so you can't do too complicated things. This mental process is the engine of his clarity. What seems like a simple restatement to him feels like a revelation to others because he has already performed the immense conceptual work of finding the most direct path He is married to a fellow mathematician and they have a daughter. He noted that the birth of his daughter in late 2013 forced him to become more disciplined with his time. He hurried to finish a paper just before she was born, remarking that he didn't get much done afterwards for a while. Mathematics, he says, is his passion and it fills the free spaces in his life, but he resists attempts to romanticize his work. When asked if he felt he was meant to be a mathematician, he called the idea too philosophical. Perhaps most telling is his own view of his work. He sees himself not as an inventor, but as an explorer. For him, mathematical truths are objects to be discovered, not created. Doing research is really like discovering certain things that are just out there, he said in an interview with ICM TV. He repeatedly states that he feels he is still in a learning phase. I'm still in the phase where I'm trying to learn what's there. To his colleagues, he is redrawing the maps and discovering new worlds. From his vantage point, he is still just surveying the coastline. Peter Scholze at 37 today produces a remarkable amount of original research. As his collaborators note, what he produces in a few months can easily suffice for a PhD. His doctoral advisor, Michael Rappaport, expressed confidence that he has still many ideas that he has to bring to fruition. His work continues to push into more fundamental territory, and the structures he has built so far are themselves just components of a still larger, unseen edifice.